Good morning, all. So today we are starting the third unit of operating system, that is process synchronization. The process synchronization, or also it is called as the concurrency control. So the topics to be discussed in this third unit, that are the synchronization between the process and thread, mutual exclusion, the principles of concurrency, requirements for mutual exclusion. Mutual exclusion means what? Then operating system support for mutual exclusion, that is in the form of Semaphore or mutex. Then the classical problems of synchronization. So classical problems of synchronizations are nothing but they are not actually the problems, but they are the examples, right? So how synchronization is achieved in the processes in the operating system, that we have to see. I mean, these are the examples. For example, reader-writer problem or the producer-consumer problem. Already we have discussed about the producer-consumer problem. There are the processes, they are of the type of producer, and there are some processes, they are of the type of consumer process. Then how the communication or how the cooperation is achieved by these type of processes, that we have to see in the classical examples of that particular synchronization. And the final and the very important topic is nothing but the deadlock, right? So deadlock means what? What is the principle of deadlock? Which are the four necessary conditions for the deadlock? Then how to avoid the deadlock? Is there any possibility to prevent the deadlock? So is the deadlock prevention is possible? Right. And if the deadlock occurs in the system, then how to recover from the deadlock? That we have to see. And we have to see to avoid the deadlock algorithm, that is a very famous algorithm. It is called as the banker's algorithm, that we have to see with the help of resource request algorithm and the safety algorithm. That means this from the practical point of view, it is a very important unit, as well as from the theory point of view or the conceptual point of view also. This unit is very important, totally depending upon the synchronization or the concurrency control, right? So process synchronization means what? I think already we have discussed synchronization means what, or the concurrency between the process. Now, as you know that there are n number of processes they are running in the system. As there are n number of processes they are running in the system, and there are limited number of resources. So it is defined like this: cooperating processes can affect or get affected by the execution of other process. That already we have seen the concept of cooperating processes, right? So the cooperating process may share data and code. A situation where several processes access and manipulate same data concurrently and output depend on the order of process, then it is called as the race condition, right? Therefore, there must be synchronization between processes manipulating the resources and do not interfere with one another. And that is called as the process synchronization, or that is the main motto, or that is the main aim behind the process synchronization. So see it carefully. Process synchronization, what is the necessity of process synchronization, or what is the aim of process synchronization, that we have to first understand. So as n number of processes, so one can say that n number of processes they are running in the system, right? So if there are n number of processes and processes are more and the resources are less, for example, if we see the processor or the CPU is only single, right? But that single processor, it is being used to execute multiple number of or n number of processes. The meaning is that what we have to do here, there must be proper synchronization between the process. Until and unless there is synchronization, these processes they fail to access that single resource, that is CPU or the processor or memory. Main memory is a single resource, for example. So if multiple processes want to access the main memory, then there must be proper communication, there must be proper coordination. Or for example, another example, some file. So file is one resource, and suppose a single file, it is being accessed by 2-3 processes at the same time. Some data it is required by 2-3 processes at the same time. So in this case, one can say that there is a competition. There is a competition between the processes to get or to acquire that resource. See carefully, there is a competition arises, or one can say that there is a competition arises between the process. For what? For to acquire the resource. So they run to get that resource. The process run to get that resource, because until and unless that process get that resource, it cannot complete its execution. For example, there is a file, there is one file, and in that particular file, one data is there, and that particular data is important for the execution of 3 or 4 processes. So what happens? So 4 processes compete with each other. They compete with each other and they run, and they try to acquire, they try to get that particular data so that they can execute successfully. So this is the thing, or this is the picture that arises in the system, right? So to avoid, and this is called as the race condition. This particular phenomenon or this particular concept is called as the race condition. So to avoid the race condition, what we must ensure that there must be proper process synchronization. So to avoid this particular race condition, one can say that, so this race condition, how this race condition arise in the system? Because there are, say for example, there is a process 1, there is a process 2, process 3, process 4, and process 5, dot 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 up to n number of processes, and there is a single resource. This particular, say I can say this is the only one resource. So all these processes want to access, to the same resource. So definitely they will race. So the race starts between the processes, and they say that who will acquire that resource first. This race condition will arise here. So race condition means there is a competition between the process to grab that particular resource. And if what happens, if there is a competition starts, if the competition starts, so one process will grab that resource, and remaining all other n-1 processes, they remains as it is without getting the resource. Getting my point or not? If there is a race condition arise, or the competition begins within the process, then what happens? Then one process will get the resource successfully, one process able to get the resource successfully, but at the same time n-1 processes, they remains without getting the resource. n-1 processes are there, they are not getting the resource. So is it so that then n-1 process, they stop their execution, right? So the question is that we have to avoid this particular problem, we have to avoid this race condition. So that's why the process synchronization is important concept, or we have to follow. In the sense, the processes or operating system has to follow the process synchronization, proper process synchronization, right? So that there must be particular cooperation, or there must be particular coordination between the process. So if a resource is there, then there must be cooperation between this n process. Yes, this process first, P1 process will first execute that particular resource, then P2 will execute the resource, then P3 will execute the resource, and P4. So some type of communication, some type of coordination is essential so as to execute the resource, and neither of the process remains as it is without getting the resource. Are you getting or not? So meaning is that why the synchronization is important. Now, see carefully why the process synchronization is important. If there is no synchronization, if there is no communication, if there is no coordination between the process, then definitely if they are not cooperating in nature, they are competing in nature, right? It is a general tendency. If they are not cooperating in nature, meaning is that they are in a competitive in nature. And if they are in a competitive nature, so they see that each one of them see that they should one should get the resource first as compared to other. So we have to avoid this competition. We have to avoid the race between the process. In the sense, operating system has to avoid the race condition or the competition within the processes. So to avoid the race, to avoid the competition, the synchronization mechanism is the key factor for this. So what synchronization is? Still that synchronization is the concept, or it is, one can say, it is the conceptual study. So synchronization tells us that we have to arrange the process, we have to execute the process in such a way that all processes get a chance, all processes get an equal chance or equal opportunity to execute with that particular resource, so that neither of the process remains as it is without getting the resource. Getting my point or not? So how this point, so I think it is clear to you the concept of synchronization. Now it is a theoretical concept. Now how the concept theoretically is implemented practically in operating system, right? So there is a code written in the operating system for the process synchronization. So how OS is able to synchronize the action of the process, that we have to see how operating system is able to synchronize, right? So the critical section problem, or it is not a problem, right? If there is a word problem, so don't consider it as a problem, but it is just an example, or critical section concept problem, or you can say it is a concept, critical section concept. So what is critical section? See carefully. It is each process has got a segment of code and it is called as the critical section code, right? Now this critical section code is to avoid the rest condition. Why this critical section? Now we can say that this process synchronization is implemented with the help of critical section in the operating system. Or one can say that critical section gives us the solution for the synchronization, or it is nothing but the implementation part of the process synchronization in the operating system through critical section. Critical section is nothing but each process has segment of code that is called as a critical section, and it is used to avoid the rest condition. CS or the critical section. In critical section, each process can change the common variable, update the table, and write into the file. See carefully, yeah? In critical section, each process can change the common variable and not the private variable. Common tables and as well as the common files it can change, means it is the common area. So at any moment, only one process executes in critical section. When one process is executing in critical section, no other process is to be allowed to execute in the critical section. That is mutual exclusion. This is important point. What is mutual exclusion? So mutual exclusion meaning in the sense that when one process, so each process, so see carefully, each process has two sections. It is a critical section and one can say the private sections. Critical section is nothing but the public section. In in object-oriented programming, in the previous year, you might have studied the members, that is the class member, that is the public members as well as the private member, right? So what is the public data member and the private data member? So public data members are the members that can be accessed by any class objects or anywhere it can be accessed in the program, and it can be accessed by any class member, public members. Those you are declared as a public variable, right? But private variable that can be accessed by only that particular class only, or the members of that particular class only, right? So this is very similar to that. So critical section is nothing but the public area. Critical section is the public area. Public area in the sense where all other processes, means it is nothing but the shared resource. Critical section, you can also refer to it as a shared resource, where the processes, they are able to share the resources. Means if a particular resource is shareable, for example file, if the file is shareable, so you can call it as a critical section. Meaning is that process one, process two, multiple number of processes, they are able to handle that resource, or they are able to access that resource, just like your public members and the private members. Private member do not have access to any other class member, right? But in case of public member, public variables or the public member, that can be accessed by any member or any class. But the same way, critical section, when one process is executing in the critical section, see the definition of mutual exclusion, always it is asked in the examination, define mutual exclusion. When one process executing in its critical section, then no other process is allowed to enter into the critical section. Meaning is that, say for example, if we write in the same manner, do bracket entry section. So entry section is from where the processes enter into the critical section. So here is your critical section, and from critical section there is exit section, and from exit section the process enters into the remainder section. So when I say that the process P1 is here, process P1 now is in an entry section, right? So when the process P1 enters into the critical section, and there is another process P2, so P2 is not allowed in the critical section, right? So P2 is not allowed to enter into the critical section. So mutual exclusion. So these are called as the mutual exclusion, or in short form it is called as ME, mutual exclusion, right? So mutual exclusion of the between the processes, meaning is that when one process is executing in the critical section, no other process is allowed to enter into the critical section, right? So when P1 is executing in the critical section, P2 has to wait, or P3 is there, for example, then P3 process has to wait here. So as soon as P1 comes out from here critical section and it is executing in the remainder section, means I can say that here are the public variables, here are, one can say these are the all your public variable, and these are your private part, or these are, one can say this is nothing but the private property of that particular process. Private property, it is a public property. Public property means that can have share between n number of processes, but the private property is nothing but the property is owned by that particular process. So the apart from, suppose here is say for example int, suppose integer a, integer A is the public variable, but in the same case, integer B is the private variable for that particular process, P1. So integer A can be changed. The value of integer A can be changed by P1, but not at the same time. When P1 changes the value, at the same time P2 has to wait. When P1 changes the value of integer A, then after some time, when the P1 enters into the reminder section, then only the P2 is allowed to enter into the critical section and allowed to change the value of integer A. Then P2 leaves the critical section or exit from the critical section, and P3 allowed to enter into the critical section, and then it will change the value of A. So A can be changed by any number of processes, as it is in a critical section or it is in a public property. But the private one, the integer B, is the property belonging to P1. So no other process rather than P2 and P3, they have access to private part or the private property of that particular process. So integer B is the private one. Getting this point? So this is the logic of the critical section. This logic is implemented in this way: entry section, critical section, then exit section, and the reminder section. Right, and do while loop complete. So each process containing 3 sections: entry section, exit section, and the reminder section. The critical section problem is to design a protocol that the process can use to cooperate. So with the help of this critical section, the processes P1, P2, P3, they are able to cooperate. How they are able to cooperate, that we'll see. Right. Now the solution to the critical section problem must satisfy the 3 conditions. Now this mutual exclusion or the critical section must able to follow the mutual exclusion, the progress, and the bounded waiting time. Right. So meaning is that mutual exclusion, if process Pi executing in the critical section, then no other process can execute in their critical section. Right. If process Pi, so critical section, this particular critical section must fulfill these 3 conditions. So which are the 3 conditions? The first, remember these 3 conditions for critical section. So first condition is that it first follow the mutual exclusion. So mutual exclusion means what? If process Pi executing in this critical section, then no other process can be executing in their critical section. This is the first mutual exclusion. So we can say that the processes are mutually exclusive, or the critical section is mutually exclusive, right? The second condition, progress. Now the progress in the sense that see carefully, progress. If no process executing in its critical section, and some processes want to enter into their critical section, then only those processes that are not executing in their reminder section are allowed for the critical section. Getting my point or not? If no process executing, see carefully, okay, the meaning of progress. If no process, so here, for example, I can take example P1 and P2, right, and P3, for example, 3 processes. How we will justify the progress? If no process executing in the critical section, no process is present here, then only allow those, and say for example, here is the P4 process. P4 is executing in the reminder section. Then only allow those processes that are not executing in their reminder section. So P1 not executing the reminder section, then it can enter, and after executing from the critical section, it can exit from that particular section, critical section, and enter into the reminder section. P2, after P1 finish its work, P2 enters into the critical section, it will perform some operation, and leaving from P2 leave this critical section and enters into the reminder section. P3 also enters into the critical section and it will do the operation manipulation and leave the section P3. Now P4 has already in a reminder section and still it demands to enter into the critical section. See carefully, yeah. When P4 is in the reminder section and still after the reminder section, it still is demanding that critical section. So what is the meaning is that P4 is in the reminder section. The P4 which is already in the reminder section, it means that it has already accessed the critical section earlier. Means it has initially or early, because when it enters to enter into the reminder section after completing the task in the critical section, then it only enters into the reminder section. Hence the critical section says that, or the rule says that, progress rule says that allow only those processes that are not executing in the critical, that are not executing in the reminder section. If the process already executed in the reminder section, it ultimately means that, or it by default it means that when it is in the reminder section, by default it has executed critical section initially or earlier or previously, right? So don't allow this P4 to again enter into the critical section. Because what happens if it do so, if the process executing in the reminder section and they are again demanding for the critical section, then there it may happen that there are so many processes, there are n number of processes, they will not get chance to enter into the critical section, right? Because they are also in a waiting, to get their chance to execute in the critical section. Getting my point or not? So do not allow the processes which has already executed in the critical section and executing in the reminder section. That is one can call it as the progress, right? And bounded waiting in the sense there exists a bound on number of times that other processes are allowed to enter into the critical section. So there must be particular bound, means there must be upper limit. So 2 times the processes are only entering into the public section or this critical section. More than 2, they are not allowed to enter into the critical section, or more than, so whatever it may be, there must be particular upper bound, or there must be some bound or some limit, so that the process cannot frequently go or frequently demand to enter into the critical section. Getting this point or not? Critical section in the sense that this is a one can say that it is a very important resource. Why we are calling it as critical? Why the name is given it is a critical? Because it is a very important resource. Say for example your CPU, or say for example your main memory, or even it can be your file, or it may be your server variable. Say for example integer a, it may be variable. So why we are calling, and this a, why it becomes so important? Because there are n number of demanders. There are n number of demanders means n processes, they are demanding that particular variable, they are demanding that particular file, or they are demanding that particular memory, or they are demanding that CPU. So it is very crucial part, because all n number of, there are 1000, the more than 1000 number of processes, they are required this particular critical, they are required this particular thing, resource, for their complete execution. Until and unless they get this resource, they will unable to execute successfully, right? So that's why the critical section, that's why this is important one, critical section. This mutual exclusion, progress, and the bounded waiting, these 3 conditions must be fulfilled for the critical section, right? Now you may ask the question that how we are achieving the synchronization, right? So yes, you can, if we see it again, if you see it carefully, you will find that yes, now the process synchronization has got achieved here. How? Because if there is a process P1, P2, P3, and P1 is in a critical section, so P2 is waiting here and P1 is in a critical section, or there is a P1, P2, P3 process, P1 is executing in the reminder section, P2 is in a critical section, and P3 is in a, say for example, in an entry state, or P3 is in a waiting state. Why? Because P2 is already in a critical section, and P2 has already executed the critical section, and it is in a reminder section, or it is doing its own job, right? So one can say that there is a perfect synchronization, there is a perfect concurrency between the process has achieved with the help of the that particular critical section. Getting my point or not? This critical section is a concept, or we can say it is a concept given, it is a theoretical concept. Now in practically how the concurrency takes place, how the synchronization, how the critical section is implemented, that we have to see. And it is implemented with the help of Semaphore. The logic is applied here. So logic is here, how to implement this, how to implement the critical section, right? So Semaphore means what? So this Semaphore is nothing but it is used to solve the critical section problem, or it is solved in the sense it is used to represent the critical section concept. Now Semaphore is nothing but an integer value s. Semaphore is generally represented by s. It is an integer value, right? Or it is a, you can have the flag, or you can have the boolean like yes or no, or flag is set to yes or no, right? Or 0 or 1, flag is set to 0 or 1, or it is a binary variable, for example 0 1. So this integer variable access through 2 operations, that is wait and signal. So Semaphore means it is nothing but a combination of 2 functions, and these 2 functions are wait function and signal function. Now what is the function of wait? So wait is nothing but the Semaphore initialized to non-negative value earlier. It is initialized to non-negative value. Then wait operation decrement the Semaphore value, that is this test. So wait operation s is equal to s minus 1, initialized to it a non-negative value. Initially, say for example s equal to 1, and if it is a wait function, so wait in the sense s equal to s minus 1, so decrement the value, s becomes 0. S becomes 0 because s equal to 1 initially. And the signal function increment the Semaphore value, that is increment s equal to s plus 1. So 0 plus 1, that is nothing but your S becomes 1. So wait and signal function, these are the two functions. So one can say that you have the traffic signal, red signal, and you have the green signal, for example, right? Red and green, right? Red and green traffic signal. So meaning is that in our in our critical section, say for example, here the given is, here I have given the code, wait, this mutex is the semaphore, the critical section, then signal, mutex is the semaphore, and reminder section, and the while one statement. So mutex is one semaphore and it is initialized to, say for example, initialize mutex is to 1. Initialize this mutex semaphore, you can define any semaphore is to 1, right? And modification to the integer value of the semaphore in wait and signal must be executed indivisibly, or it is also called as the mutually exclusive. The semaphore is mutually exclusive because we are implementing the critical section. What we are doing here, we are implementing critical section practically, right? Critical section concept we have defined, or we have understood the concept of critical section. Now how to implement the critical section practically, that we have to see. So when one process modifies the semaphore value, no other process can simultaneously modify the same semaphore value. So what is the meaning of this? The meaning of this is that the semaphore is mutually exclusive, or S value. S value, or here mutex is given. Mutex means mutual exclusion. Full form is mutual exclusion. Mutex is the semaphore. Any value you can define, or any variable you can define as a semaphore, mutex, and it is mutually exclusive. Means only one process at a time can have access to change that particular variable. Only one process can have access to change that particular variable. For example, see here, wait mutex. So initialize to 1. So wait 1. So wait 1 means what? Wait 1 means what? Wait 1 means S equal to 1. So mutex equal to mutex minus 1. So that value becomes now 0. That value becomes now 0. So P1 initially come into the system and P1 want to execute in the critical section. Process P1 wants to execute in the critical section. So P1 definitely enters into the critical section and start executing the critical section. At the same time, P2 process enters into the system. At the same time, P2 process enters into the system, and the value of mutex is equal to 1. So P2 make the value of wait is equal to 0. So wait function tells that, very simple word, wait function tells P2 process to wait. Means it is just like your red signal. Wait process, or it is nothing but the red signal, means process P1 is already executing the critical section. So all other processes, they are demanding to get into the critical, they have to wait. So wait function tells that, or it is just like your red traffic light. Means the processes wanting to enter into the critical section, they are not allowed, they have to wait there because some process is in the critical section. Now when process P1, see carefully, when process P1 completes its task or executes completely, then it enters into then it executes the signal function. Now the value of mutex is equal to 0. Now it has become 0. So signal mutex means signal is 0 plus 1. 0 plus 1, that becomes S equal to 1 now. S become 1. So signal means it is your green light. This is your green light. So P1 gives the green signal that I have come out of this critical section, and the next process can now enter into the critical section. See the working of the semaphore, how the critical section is implemented with the help of semaphore, right? So you can see it from the diagram or from this pseudocode that, for example, if P1 is in the critical section and P2 is here, so P1 has already changed the value of this mutex semaphore. P1 has already changed the value of this mutex semaphore and the value is now 0. So meaning is that wait function indicates to the process P2 that it has to wait, right? Wait function indicates that particular P2 process that it has to wait, or it is the red signal. You cannot enter, right? As soon as P1 process completed its job in the critical section, as soon as the P1 process completes its job in the critical section, then it execute the signal function. Execute signal function means it has to just increment the value of the mutex semaphore, that is 0 to 0 plus 1 is equal to 1. So as it will change the value of mutex semaphore 1 and enter into the reminder section. Reminder section means what? P1 go to perform its own task, whatever it may be the task it has to perform, and the critical section now becomes free. As soon as this particular section becomes free, as soon as the P2 comes to know that the value of semaphore now changes to 1, as soon as it come to know that value of semaphore becomes 1, So it receives the signal that is nothing but your green signal. Then and then only the P2 again enters into the critical section and start executing in the critical section. Start executing the code in the critical section. Getting this point or not? So this is the way. How the synchronization, one can say that the synchronization is achieved with the help of this critical section or with the help of this semaphore. That's why, from the practical point of view, also the semaphore is very important. From the practical, you have to implement, you have to write down the program for the reader writer problem or for the producer consumer problem with the help of this semaphore concept, right? So this is the way. Weight weight is nothing but your red light, or it is nothing but the red signal, and the signal is nothing but your green signal, means it is nothing but a green light which tells to the other process. Green signal is nothing but a green signal to whom? Green signal is to other process. Now yes, the critical section is now free, it is now empty, you can have access, means now you can allow, means only one process is allowed. Red signal means what? Stop. The process, the new process has to stop because there is some process that is executing that particular critical section. It is very simple. There is nothing difficult in the logic, but you have to just understand how the code is written actually. The mutex code, one can say that mutex code, or the you can have wait S, then critical section, signal S, reminder section, or while one. So we can have the binary semaphore value, the semaphore with an integer value that can range only between 0 and 1. So this semaphore value, it is initialized to 1, it is changed to 1, it is initialized to 1, it is changed to 0, and again it is set to 1. So this is the way how the wait and signal signal 2 function works in the system to achieve the critical section, to achieve the process synchronization, right? So I think this is clear to all of you. Now we'll move to the next point. Okay, so this is nothing but the classical problems of synchronization. Problems, do not consider it as a problem, but you can call it as examples, right? These are nothing but the classical examples of synchronization. Though in the reference book they have used the term that is problem, but it is not actually the problem. There is no problem at all. It is just an example, or one can say that yes, it is just an example. How the synchronization is achieved, which are these are, we can say, the classical types of synchronization. You can also call it as a types or examples, right? So classical types or the classical examples of synchronization. So synchronization, so we have already seen the producer consumer problem, or producer consumer type, or producer consumer example. So producer consumer example, so already we have discussed that there are the processes, they are of the type of producer type, and there are some processes they can be categorized in the type of consumer process. So producer are the process, they go on producing some data, they go on producing some information, and the consumer are the process, they go on consuming the information that has been produced by the producer, right? So if you want that there must be a proper synchronization, there must be proper communication, then producer and consumer must be synchronized properly, right? So one or more producer process generate data and place in the buffer. So we can have, say for example, this is the producer process, this is the producer process, and this is, one can say, it is a buffer. Already we have seen the buffer capacity is a bounded buffer. There is no unbounded. Unbounded is a theoretical concept, but there is a bounded buffer. So producer is producing all the things, whatever it may be, the data information it produces, and it will place inside that particular buffer. At the same time, consumer process try to consume the data. Consumer process try to consume the data which is placed inside the buffer. So this is one process. Say for example, this is process P1, P2, P3, P4, and these are the process. Suppose P10, P11, P13, P14, like these are. These are 4 process. They are categorized as a consumer process, and there are 4 process. They are categorized as a producer process. Just like we have seen the example that is, say for example, compiler produces the assembly language code and given to the assembler, and it will be then executed. So output of the producer process given as input to the consumer process, and there is a buffer. Buffer is nothing but the temporary storage where whatever may be the data that has been produced by the producer process is kept here inside, and from here the consumer go on consuming the data, right? So what exactly is the problem, or what exactly is the example that we'll see, right? So the example is that the bounded buffer, the producer only produce the items when there are empty slots. Of course, that is correct. Say for example, this is buffer. So this is buffer, or we can have. So this is the buffer capacity, or you can assume it as a queue, and this producer is producing, and it is putting the item here, and consumer is here, and consumer is gone consuming out item, means it is removing. In simple order, it is removing the items from the queue. So we can say that producer only produce the items when there is empty slot. So I can say that if this slot is not empty, all these slots are occupied, means already data has been produced and is kept here inside the buffer. So where to keep the new data? Where to keep the new data that has been produced recently? So that's why it is said that producer only produces the items when there are empty slot, means there must be space available inside the buffer. That is very clear concept, that if the space is not available, producer is not allowed to produce the items. What happen if there is no space available and still producer is gone producing the item? Then definitely the newly generated data, newly produced data, that there is a chances to lose that particular data, right? The data may be lost because there is no space to store that data. Consumer consumes only produced items and wait when the no items are available. So it may happen that consumer may consume all the items, and at a time it may arise that the buffer is empty. There is no item here for the consumer to consume, right? So these are the two things. So how to achieve? So our question or our interest, our focus is to achieve the synchronization between these two parties, that is producer and consumer. Our intention or our focus is to achieve the proper synchronization between the producer and consumer with the help of this buffer, right? So see here how we can achieve the synchronization, how we can achieve the concurrency or the coordination between this producer type of processes and consumer type of processes. So the solution to the producer consumer problem satisfy the following conditions. So there must be some condition that must be satisfied. Which are the conditions to fulfill the to achieve the synchronization, right? So our question is that we have to achieve the proper process synchronization between the producer type and consumer type of processes. So how it is possible? We have to follow three conditions or the three steps. The first step tells us that producer must not overwrite a full buffer, right? So meaning is that first is nothing but first condition is with reference to producer. Producer must not overwrite a full buffer. So this is the first condition. Second condition is consumer. It is with reference to consumer. Consumer must not try to consume an empty buffer. So if the buffer is there, so this, say for example, this is the buffer, right? And if the buffer is full, so meaning is that if the buffer is full, producer has to wait for the producer, and for consumer, if the buffer is empty, consumer has to wait, right? So if the buffer is full, the producer has to wait, and his buffer is empty. See, these two words are important. If the buffer is full, producer has to wait, and if the buffer is empty, the consumer has to wait. Getting this point, right? So what happen if the buffer is full and still the producer is go on producing? Definitely there is a chances of loss, because no space is available to accommodate the newly produced data. So whatever may be the data produced by the producer, that will automatically get lost here. And what happen if the consumer is trying to grab the empty buffer? So if there is a buffer, there is no item at all present in the buffer is empty, but then still the consumer is trying to consume the buffer, meaning is that the consumer enters into the some loop there. Consumer is trying to grab the empty buffer. That means consumer is entering into the some looping there, right? So, and the third condition, so this is the restrictions. One can say that these are the restrictions, or one can say these are the limitations that are now we are applying to the producer and to the consumer. And the third limitation, or the third condition, or the restriction is that producer and consumer must access buffer in mutually exclusive manner. Clear? What is the meaning of mutually exclusive? Meaning is that producer and consumer must access the buffer in mutually exclusive manner. Meaning is that this buffer, now this is nothing but your critical section. Getting this point or not? This buffer is now becoming your critical section. Say for example, if this is your critical section, so see again the architecture. Here is your entry section, right? This is your entry section. Then this is your exit section. This is your exit, right? This is your exit, and this is your reminder section. Right? So if there is a producer and consumer. This is the P type of process, and there is a C type of process, means producer and the consumer type of processes. And this buffer is, we are calling it as now critical section, because it is a shared resource. See carefully, this buffer is the shared resource, as it is getting shared between the producer and the consumer types of processes, right? And this producer and consumer must access the buffer, must access this buffer in mutually exclusive manner. Meaning is that when this particular producer is producing and keeping item, keeping item in this particular buffer, then consumer process has to wait. And if the consumer process is consuming the item from that buffer, then the producer process has to wait. Getting this point? That is called as the so this buffer is our critical section. Are you getting the concept of the critical section? And the synchronization is this way, right? So this is the way how the synchronization between the producer process and the consumer process is achieved, right? So this buffer is the critical section, and this is achieved with the help of the producer process and the consumer process one by one. So if the producer is producing and putting the items in the consumer, in the buffer, the consumer has to wait. And if the consumer is consuming the items from the buffer, the producer process has to wait. This is the very simple concept. And here is the pseudo code is given for the, because there is an examination, they generally ask, implement the producer and consumer problem with the help of semaphore. So this is the semaphore. We have to define two semaphore here. So mutex is one semaphore defined, right? So pseudocode, assume that there are n buffer, each holding one item. So buffer we have to define, and buffer is nothing but our critical section, or it is nothing but the resource. So mutex is one semaphore for mutual exclusion, that is equal to 1. So this mutex semaphore is for third condition. Mutex semaphore, it is mutual exclusion between the producer and consumer. It is assigned for third condition. And empty and full. So empty is for second condition, your consumer, and full is another semaphore for your producer. Remember this point. Huh? So for each condition, we are implementing three different semaphore. Full is the semaphore for to check your producer, and empty is the semaphore to check your consumer, right? So semaphore counts number of empty and full buffer. So initially empty is equal to n, because we assume that all the buffer capacity is available, and for full equal to 0. Initially it is not full, it is empty. So producer process, how to write the producer process code? So produce an empty, produce an item in next p. So the pointer next p is pointing to that particular queue here. So if I assume it is a queue, buffer queue, so you are producing and putting item here. So wait empty. So wait empty means decrement 1 unit buffer. Then wait mutex. Wait empty means you are decrementing the empty. So initialize the empty is to 1 n. So initialize it to 1. So decrement it by 1 means n minus 1. Then add next p to the buffer. So the next p pointer moves in this particular direction. So meaning, and then there is a signal mutex and signal full. So as soon as the next p pointer moves in this right hand side direction, meaning is that the producer is gone producing and adding item into that particular buffer. Getting my point on? So this code indicates that we are producing, the producer is producing the item, and it go on adding from this left hand side to right hand side. That's why the next p buffer is there, add next p to the buffer, meaning is that initially the next p is here, now your next p is here. You are decrementing the value of empty and you are incrementing the value of full. See, you are decrementing the value of empty and you are incrementing the value of full here, right? And the consumer code, for the consumer code, what you have to exactly reverse way, wait full. Initially the wait full means you have to execute the full, what is the value of full here. So you have to wait means what? Wait decrements the value, right? Then wait mutex, then remove an item from the buffer. So from this side, you are going to remove with the help of this next C, with the help of this next C pointer, next. Next C means it is a pointer of consumer, and next P is nothing but the pointer of producer. So it is go on consuming the item from the right hand side. So signal mutex, then signal empty. So consume an item in next C, and while one complete. Right. So this is the pseudo code. So see carefully, try to understand the code. It is not very difficult. Just draw the diagram of buffer here, and draw the producer and consumer, and draw the pointer next P on the left hand side and next C, and try to execute this code. You will be able to understand. And it is very simple. There is no rocket science in the pseudo code at all. Right. So this is a simple way. So this is one example. how to achieve the process synchronization and critical section with the help of the producer and consumer type of processes. Means if there are the processes, they are the type of producer type and the consumer type, how the synchronization has got achieved. This is one example. So remaining there are another examples are there that we'll see in the next lecture. So there is example of reader writer problem, the same way the reader writers problems are there, and there is a dining philosopher problem that we'll see in the next lecture, right? So you have any doubt, you can put me in the chat box.